This is the talk, How I Solve Sparse Rulers. I'm Ed Pegg Jr. from Wolfram Research. I'm going to be talking about sparse rulers. If I can get to my abstract here. So here's an example of a ruler with 6 marks, 0, 1, 2, 6, 9, 12. And with those marks on a ruler, you can measure any distance 1 to 12. For example, you can get 8 by 9 minus 1. And one question is, what is the minimal number of marks for a general length? And one thing I managed to show was that the formula square root of 3n plus 9/4 rounded gives a very good approximation of the number of marks needed. And if you subtract the number of marks needed, if you subtract that formula, you'll always get either 0 or 1. So let me talk about something completely different for a moment, and that's graceful graphs. With a graceful graph, you basically have a set of vertices, and you label the vertices with numbers so that the difference is a value 1 to n. And for example, all the values 1 to 12 are within this graph. And this is basically the same as my graceful graph, or same as my sparse ruler here. So one opening question for how this problem can solve something that's seemingly very difficult is, what's the smallest graceful graph that has a valence of 7? This graph has a valence of 4. All the various vertices have 4 edges. Well, how can you do that so that the graceful graph with the graceful edge labeling, every vertex has valence 7? Well, one way to do it is you can generate graceful graphs by looking at all permutations. For every permutation, there's a graceful graph that goes along with it. So just by going to, say, 35 factorial permutations, you could get the graphs with valence 7. And it turns out that if you use sparse rulers, these are examples of sparse rulers here, and this one here, you can use this sparse ruler to get a graceful graph with valence 7. And it looks like our attendees have stabilized, so I'm going to start the talk. So here's an example of a sparse ruler, 6 marks. We can measure any distance 1 to 12. And this formula here, the square root of 3n plus 9/4 rounded, gives a very good approximation to the number of marks needed for a graceful graph. So here's a longer sparse ruler, and all the distances from, in this case, 1 to 214, you can use this ruler here to measure that distance. And we can show that nothing is missed by doing all the subsets of 2. And there are certainly unique values like 7. There's only one way of measuring 7 with this graph, and that's using these sets of 1s at the start. But there's also a lot of repeats. For example, 8, a distance of 8 is repeated along a lot of times. A related object is a Golomb ruler, where all the differences have to be different. You can't repeat anything, but it's also okay for things to be missed. So we can check that for this Golomb ruler, which has a similar length, that nothing is repeated. And then we can, oops. Nothing is repeated. The maximum length of any difference is 1, but there's a whole bunch of different values that are missed. Like 91 is not represented as a distance in this Golomb ruler. And a third related object is a different set, where you're basically using a modulus, and in that case, all the distances can be different and none of them can be repeated. Basically, it's a one-for-one thing, and different sets are very useful for extreme graphs of various sorts. So different sets, Golomb rulers, and sparse rulers are all related. But there's a lot more sparse rulers than anything else. Here's a little bit of history. Sparse rulers were worked on by some of the biggest mathematicians of the 1940s through 1970s. John Leach, who developed the Leach lattice, made one of the first bounds for the problem with the paper in 1956. And in 1963, a person by the name B. Wickman pretty much solved the problem, which I'll get into later. And I don't know anything about this person. I don't even know what their first name. I don't even know whether B. Wickman was male or female. Let's see. In 1967, Golomb rulers were investigated by Rumson and Bernstein, and they found various ways of using affine planes and projective planes to, hi Tycho, to, yes. You really want something, huh? That's the fun of at-home conferences. You're not going to stop, are you? I know. Yes. Well. Hi. All right. Okay. So, and they've managed to come up with very good ways of constructing Golomb rulers based on affine and projective planes. And Atkinson and Hausenkluber managed to extend these methods, and they got some best-known Golomb rulers up to 100 marks. Yeah, I practiced this a whole bunch of times, and my dog never bothered me during those practice sessions. Once all those Golomb rulers were constructed by combinatorialists in the 60s and 80s, distributed started one of the biggest distributed computer networks in the last decade. And with about 10,000 hours of computer time, they managed to basically verify that the combinatorialists were correct. They managed to basically find no new results at all. So basically all this computer time that was spent on Golomb rulers was pretty much wasted, other than verifying some known results. R.C. Robinson then in 2014 used a big cluster of computers at Intel to look at sparse rulers up to 25 marks, which would get a length of 213. I'm trying to get to the next slide. There we go. So sparse ruler 13, or hopefully we're going to release version 13 soon. So with a length of 13, 5 marks is not enough. And you can basically prove that because choosing 2 items from 5, there's only 10 ways of doing it. So you can't do everything. But with 6 marks, that would be 15. So maybe it's possible. And it turns out here's the solution right here. And there's 2 items that get repeated with this list. So here's various ways of showing that this ruler, 0 to 13, meets all the values 1 to 13. Here's a longer one for length 50, and any 2 values will get some number 1 to 50, and here's all the various ways of doing it. Here's a way of showing it. So the differences of this particular ruler are 1, 2, 3, 7, 7, 7. Another way of expressing that is 1, 1, 1, 2, 1, 3, 5 7s, 2 4s, and 1 1. So these are the differences here and the repetitions. And I call this the split form. I call this up here the difference form.
And B. Wickman came up with this way of constructing rulers based on differences and the repetitions. And I call this a recipe. This is the original recipe by B. Wickman. And by plugging in, say, 1 and 5, you can get this ruler we just looked at for length 50. With a slight variation, you get this other ruler, which has a length 1 less. And I found thousands of recipes sort of like this in my research into this problem. We can convert from the plain ruler to the differences to the split form with these various simple programs. And at the bottom here, here's one way to express that ruler, the recipe at the bottom and the difference and repetitions at the top, but shown as a power. So here are a variety of Wickman rulers using this original recipe for your different R and S values. And here's the split forms you can get up to length 213. And one of the things that was verified by the big cluster of systems at Intel was that all of these rulers here were optimal. This was the longest sparse ruler you could make with these number of marks. And in 2011, a lot of attention was paid to this particular ruler. This is the last optimal ruler, which is not a Wickman ruler, the last known. And Peter Lushny conjectured that this was basically the last sporadic ruler that would ever be found. And so far that's proved to be true, but it's not completely proven yet. And this is kind of where I came in. And a few years ago, I just wanted to get the Robinson results because they'd been published in various places. Here's some optimal results. Here's what we know about them. So I asked, hey, can I see your data? And I found that all the data had been thrown away accidentally. So that didn't feel very satisfying. I was already interested in this problem, but I also didn't have a giant cluster of computers I could play with. I suppose I could have gotten one, but I didn't want to to have our company spend a lot of money on it. And I looked at this sequence here. It's a very strange sequence because it doesn't rise and it starts going up and down. So I figured, well, if this conjecture by Lushny is true, it's all ruled by Wickman rulers. So perhaps I can just use that to come up with some sort of bound on the problem. And when I tried that, all the known results came out to be 0 or 1. And I wondered, well, what is this bizarre pattern of zeros and ones? And I played around with it for months, trying to figure out what this pattern of zeros and ones was. And it just didn't make any sense at all until I went back to Wickman rulers again, and I used the values that we showed before to use floor values. And when I did that, everything started lining up nicely. I defined the excess value using this 3n plus 9/4 formula. And when the excess value was 0, it was gray and 1 was a bold. And this seemed to be a very nice pattern. And I developed a program based on Wickman ruler recipes and some other recipes I'd found, and also just kind of playing around with existing rulers that were still known. We had data up to 100, length 100. All the data from 100 to 213 had been lost. But many of these rulers are very similar to each other. If you've got a difference of, say, 7 somewhere, well, if you repeat that distance of 7, you can often get another sparse ruler. So basically, just by making slight changes to the split form, you could get a new sparse ruler. So I had various programs to just mess around with these rulers in all sorts of different ways possible. And I decided to look up to 10,000. And when I plotted out the results, I got this strange pattern, which Neil Sloan of the sequences database called see, dark mills on a cloudy day. And this is kind of a definite pattern, and it kind of helped drive what we could expect to see in the problem. Now, this isn't the pattern I came up with originally, because all the excess values here are either 0 or 1. When I originally did this, there are also some 2s and 3s, because a lot of these sparse rulers are very hard to solve. But I figured I could get everything down to 0 or 1. Eventually, I managed to solve everything that Intel had, and some of them were very difficult to find. For example, 178 took months to find. These are some of the unique solutions so far that are known. Everything that's above 213 is not proven. So these values here, these are the difficult unique values up to 213. There's also some simpler ones, which are basically Wigman rulers. And these are some difficult cases above 213 that I managed to find with my programs. The hardest one to find was this one, 1792. That was kind of a difficult value for a year before one of the programs that I had running every night on an old 15-year-old laptop, it finally came up with a solution after a whole bunch of different iterations of randomness. And with that, I had all the 0 or 1 excess values for everything. Because, well, first here's a few sequences that are based on this. And we can go into various Wigman-like results. Oops. Here's 300 and something recipe, and there's a demonstration that has these. If the dot is in black, that means it's an excess 1 ruler. If it's in the white area, like this is a recipe, and the red dot is currently showing a length 661 ruler. And here's you probably can't see that, but these are the differences and the ruler marks for that particular ruler using this recipe. I found a whole, well, 300 and something Wigman-like recipes. And I need to figure out how to go forward a slide. There we go. I also made this demonstration that shows a few thousand Wigman, or a few thousand sparse rulers for all lengths. And in the data for this talk, I've put together all the data I have for almost 3 million sparse rulers and all the various programs that I use to find them and jigger them around randomly. So we can basically, this is just a tiny percentage of all the sparse rulers that are in the database attached to this talk. So once I figured out that it was easier to solve large values. Excuse me for a second, I need to cough. Sorry about that. I found that if I just added a mark at the end of a Wigman recipe, I could get another sparse ruler very often. So one way to see that is, say I take rulers of length 520. 520 is the length for one of the Wigman recipes. So 520 plus X. Well, with plus 13, here's two sparse rulers that can be made. But for plus 12, you can't do anything by adding an extra mark at the end of a Wickman ruler. But I found that as you get to higher values, you could always just create a sparse ruler that worked out of an existing simple Wickman ruler recipe. So for the length 25,000, it doesn't quite work because 25,394, you can't make a sparse ruler of that length just using this simple recipe. But for anything above 13, anything above a length of 300,000, you could. So the proof that I found everything was basically big values are easy, solve the small values, and the proof is done. And so the hard part was really solving the small values, and that took a year. Let's see. So here's my access value formula. One thing that's not proven is whether the excess value can be -1. I've shown a whole bunch of different cases where everything is either 0 or 1. We haven't proved that it's impossible for the excess value to be lower. So we don't have a proof of the Wickman rulers being the best case for optimal sparse rulers. If the Lushny conjecture is correct about the ruler of length 58, then this is true, and the problem is completely solved. If there are cases of sparse rulers which violate this conjecture, then there's also a whole bunch of other sparse rulers that can be generated from the smallest case that's a counterexample. It would basically cause a big splash in this dark Mills pattern. And it's been proven that there is no such case of length 213 or less. I don't think a counterexample exists for this, but I don't have a proof yet. I've mentioned I've put the data on the database, and it's almost 3 million sparse rulers. So here's the last non-Wickman optimal ruler. That's this one here of length 58. Here's the last one based on 3 differences. It has length 69. Here's the last one that has a greatest difference of 12. That has 181. And this is the last ruler that has just 4 different differences. If you use 5 different differences, there's basically no upper limit. You can get sparse rulers of almost any length. Here's the last one known that has 5 difference in the split form. Has length 262. Here's the last known ruler where no adjacent values repeat in the difference form. Whether there's another one of those is unknown. At the bottom here, this ruler of length 582, it has a big gap in it, much like this big gap here. And this is the last known big gap ruler where there's a gap in the sparse ruler that's greater than 1/3 of the ruler's length. Whether there's any more of those are unknown. And this value 582, this is what's called a cloud value. Let's see if I can go back here. These values that are up here, these are what I call cloud values. This is the dark Mills over here. I think it's unlikely that we'll find anything really spectacular down in this area because it's kind of very highly driven by Wickman ruler recipes. But up here, things are considerably stranger. And 474 is the position of the first case that's in the cloud. I have like no confidence that that XS1 value is actual. I have a feeling that all these cloud values might all be 0. They're just very difficult to find solutions. However, you would take like 1 billion years of computer time to crunch down 474 to look at all cases. It's a very difficult combinatorial problem, and it might not solve anything. It might find anything. So it's possible that these upper values here are correct, but I don't have any faith in them. So thank you very much, and I can take questions. I know I went through that pretty fast. Apologies for the dog. Let's see, you can write to me at edp@wolfram.com. Well, one of them, what are some applications for sparse rulers? One of them is radar arrays. If you set radar array detectors up at these distances, you basically can be sure that for any distance you want between the arrays, it's represented somewhere in your array facility. And so if you're basically wanting to cover all possible distances from 1 to 213, you can use just 25 arrays to get all those different distances. I was talking about graceful graphs earlier. If you use these sparse rulers, you can get a handle on high valence graceful graphs, and it's kind of a upper bound for everything that's within the graceful graph problem. There's relations to Golomb rulers and projective planes. I've managed to create a whole bunch of different graphs with these sparse rulers that basically whether a graph exists or whether it does not exist. In fact, we've added to graph data, we've added a graceful graph property, and some of the sparse data research was very useful for determining whether graceful graphs exist for many different graphs. My dog is what breed is my dog? My dog is a German Shepherd. Is there equivalent of sparse rulers in 2 dimensions? There is, if you go to demonstrations, there is it's called the distance problem in 2 dimensions. And that basically, actually that one is looking at whether all distances are different. You basically want to go to square roots for 2 dimensions because you can represent distances very easily on a lattice with square roots. I'm not sure whether anyone has looked at whether or not all possible, whether, for example, in a 7x7 lattice, you could get up to square root of 98 distance, I believe. Whether there's a set of points that covers all possible lattice distances within that lattice. That would be an interesting problem. I'll try to look at it. All right. Many thanks.